piling platform design and construction. So let's peel it right back to what we're looking at here. And what are piling platforms? The purpose of a working platform is to provide a safe and durable work surface from which piling and pile rigs and plant can operate. And there's quite simple structures that are used widely across the industry to ensure that plant remains stable whilst in operation, essentially. They're often designed for piling rigs to begin with, but then used for all sorts of plant as well as follow-on trades such as foundations for scaffolding. And the main criteria is that they must enable plant to remain stable whilst operating and tracking. They must not deform excessively under load, and they also must be robust to enable prolonged use in some cases, and must allow plant to operate properly as well, which includes allowing the tracked plant to sprag, which is where they kind of move the tracks in opposite directions and kind of turn on a sixpence. Other criteria for working platforms may be to provide a minimum CBR for foundations of the permanent works or the ground bearing slabs. They could be a base for other loadings such as scaffold foundations, as I've mentioned. And lastly, they can also act as a contamination capping solution on remedial sites, which is a great advantage that we've worked on a couple of schemes with remediation contractors, because it's worth thinking about how this mat can work harder and double up or even triple up on its uses. And it really doesn't have to be kind of a standalone design, because if we get the planning right and we get our temporary works to do as many different things as possible, then that means that the site operations are going to run as smoothly as possible. There's lots of information out there on the design and construction and also maintenance of working platforms, which can be used by designers and contractors alike. A publication by BRE 470, which is shown here, working platforms for track plant, and also the working platform guidance provided by the Temporary Works Forum. They're great guides, but there's others available, such as the Syria document 123, and further research carried out by BRE as well as manufacturers of the Geogrids too. So let's look at different types of piling platform. I'm going to run through the main piling platforms that we've used, and you've heard of like the big three that are typically used, being pure granular, also known as a unreinforced mat. We've got a Geogrid reinforced and also a chemically stabilized mat. Piling rigs can also run on existing concrete slabs or timber mats without a granular platform, and I've previously justified a pile rig operating on proposed raised slabs with piles that are sleeved through that raised ground floor slab, so the rig can essentially pile down through a basement without even entering the basement. But we're not going to cover these as they're all very project specific. So you've heard of the big 5 safari animals in the African plain, like your elephants and your rhinos and your lions and things. But here we're going to discuss the big 3 in the world of pile mats, and we're going to tell you all about them. So continuing on that kind of safari theme, mat number 1, we're going to look at a very common animal, and this is a basic and simple in construction, essentially putting down some decent engineered fill to improve the bearing capacity of the ground. It's a pure crush granular mat. Its design and construction is pretty well established, and there's great guidance provided by BRE, among others. That their working platforms for track plant document BRE 470, which I showed you earlier, is great, but it's limited in its application. For example, it cannot be used for very soft soils or very stiff soils. And designers, including ourselves, have streamlined some of these methods in the document to make a more efficient design. So some of the pros of this platform is that it's simple to build, it's inert and easy to maintain, and there's opportunity to reuse Site 1 material that may be in abundance. If you have just demolished a multi-story concrete frame structure, for example, you've got lots of that crushed concrete available, so you can pop it all in the ground for your pure crush granular mat. The main negative is that it generally provides the deepest mat overall. So before we go on to another type, I'm going to briefly cover the kind of information that we'd require to design a granular mat, which also lends itself to the other types as well. And these are the loading information for the pile rigs or plant that you've got, so which are typically provided in the BRE 470 format. the load cases. These are often provided by the piling contractor. The area, so that where the piling works will be carried out, which is typically shown on a drawing with a proposed pile level or PPL. And also something crucial is the site investigation report, in situ site tests, borehole logs, etc. This tells the designer what the ground is like and will drive the thickness of the platform. Because understanding that ground profile of the soil that we're working with is really a key requirement, and this is the foundation of a platform, is the ground that you've got on site. And an accurate understanding of that soil strength is the only way that you're going to produce the right design. Because if you don't understand the problem, then you can't provide the right solution. Here we can see an example where I've shown the proposed pile level across the varying levels of sites, and this shows what kind of soil that we're going to be forming our pile mat on top of, and also where the groundwater levels are, because groundwater levels can have a significant impact on the strength of the ground underneath the mat, and it's not something to be taken for granted, and we'll see why a little bit later. I've shown on screen a typical design output relating to pile mat design, and then as a minimum there needs to be a detailed description of the required construction and associated designer's risk assessment too, which is essentially forms a part of the specification and accompanying DRA, if you will. The next output is a working platform certificate to hand over to the piling contractor. And these documents describe the construction requirements. They highlight any residual hazards and specify the required testing that is to be able to bring the mat into use. Another potential design output is a drawing showing the mat extents. However, for simple schemes, this is usually just a quick sketch showing where the mat is going to go. And now on to our next mat type. And for this, I'm going to hand over to Craig. So Craig, over to you.
Yeah, thanks very much. So everything that you've just discussed there relates to everything that I'm just about to discuss too. So you mentioned the impact of BR470, especially in terms of the unreinforced thickness. That document does actually give you scope to use geosynthetics, but the performance of those geosynthetics in terms of thickness reduction is quite limited. So we depart from BR470 and we have our own method of analysis. If you go to the next slide, please. So the working platform document here from the Temporary Works Forum does actually highlight that there are other methods available. Go to the next one. And our method is what we call the reinforced soil raft method. We look at the application of the granular materials in conjunction with our high modulus geogrids. It's based upon the Tsagi method, and we look at the improved bearing capacity of the granular materials. As is shown there, BR470 does permit alternative methods. So some people, when they use BR470, they look at the reinforced thickness and they think that is an efficient use of some of these geosynthetic materials, but it's based upon the 50% of the QC strength of those materials, not actually the performance of those materials, the true performance. So what the geosynthetic materials do is increase the angle of load spread. So if we look at the top right image, you can see there that without the geosynthetic material, you have what's typically a 1 in 2 angle of load spread. By introducing a geosynthetic material at the subgrade, you can increase typically that angle of load spread up to 1 in 1. So you can either carry a greater load or you can work over a weaker subgrade with the benefit of that increased angle of load spread. Or if you've got the same contact area and the same subgrade and the same load, you can actually take that thickness and reduce it. And a typical thickness reduction is 40 to 60%. So on average, we're reducing thicknesses of working platforms by around 50%. As you can see there, and as has already been mentioned, the assessment of these working platforms is critical. In particular, we need to truly understand what the subgrade is and where those values are taken from. On the smaller projects, we tend to find that you get a very limited amount of information. On the bigger projects, you sometimes find that there's a lot of information, but it may not necessarily be in the right location for the working platform. So it's really important that we have the detailed information through the assessment of a design brief so we can actually carry out the analysis, because the consequences are significant. So when we carry out our assessment, there's several factors which Josh has already mentioned. So the type of plant, the foundation soils, the working platform material itself, the geogrids and the geotextiles used. So in terms of the plant, we need to understand what the short-term construction loads are. So as the platform is being constructed, we need to understand what axle loads are going to be utilised. And you would anticipate that the vehicle on the right has got the greatest damage to the platform material, but actually it's the vehicle on the left, because you've got a smaller contact point and very high tyre pressures, whereas the vehicle on the right has got a large contact area and they use what's called flotation tyres. So we need to understand how the platform is being built before it's being utilised. Then we need to understand what plant is going to be working across that platform zone, and subsequently understand any other plant that's going to be working across that platform after the lift or the piling operation has taken place. So as you can see there, that you wouldn't anticipate that that would be much of a load, but actually when you look at the size of the outrigger plates, you've got a very small diameter plate and you've got an eccentric force going through that small diameter plate. So it's very important to understand, after you've done your piling operations and your lifting operations, how it's going to be used in its serviceable condition. You also need to understand where the soils data comes from, because where you've got the very large project, and in this particular case, this is Thames Valley Viaduct on HS2, extensive amount of soils information, but you need to be very specific at the location of the working platforms. When you've got multiple working platforms, you need to be monitoring those working platforms during the progression of the project. In this particular case, it's in the Thames Valley flood zone. So the viaduct itself is a one kilometre long viaduct, and the piers have to be installed. And to install those piers, you then have to put piles in place, and you need the working platforms in place. So at every single location, the ground condition may vary. So as well as having all the site investigation and the ground investigation to hand, as you expose the ground, you need to understand what the subgrade condition is like at the time of exposure, because it may be that that has been in flood and the moisture susceptible clays have changed over time. You also need to understand how the soils data relates to the typical section. So not just in plan, have a look at the typical section, because this is a working platform, but this is a working platform sat on a 14-metre high reinforced soil structure. So the impact of the ground conditions has a significant effect on the internal global stability of these sorts of structures. So it's really important to understand the geometry and plan and section in relation to how the soils data is offered. The next most important aspect is the platform material itself. So this was on, Josh, you mentioned about nuclear. This is the Hinkley Point C contract, the electrification works. And this is a tier 1 and a tier 2 contractor who are very experienced people on sites. They understand what a well-graded granular material is from a quarried source. So that's gives you a good idea of a very competent granular material that works in conjunction with the geogrids. On the next slide, you'll see this is a not so competent tier 3 contractor on a very small site, getting access to some recycled materials. So Josh, you mentioned about some of the brownfield sites where you've got some real good quality crushed concrete. That's a great platform material. What you can get on some projects though is what's classed as a 6F2 granular, but in my eyes, it's just building waste. You can get a real mix of materials in there. So you've got bits of cloth, plastic, timber, glass, and that inconsistent quality across the working platform can have a detrimental effect on the performance of that working platform.
Sometimes it can go the other way. I've seen it where 6F2, it looks more like talcum powder, you know.
I mean, that's it.
Yeah.
When it goes through the crushing process, the recycling process, it goes down to dust.
Yeah.
And when the weather is in your favor, it's not too bad, because it especially concrete, it can become a little bit cementitious. It can be a really good material to work with. But when you've got a very, very high fines content and it rains, that's an absolute nightmare. And the HS2 project that I mentioned, that's in a flood zone. So if you're underwater and it's raining, you've not got a very good scenario there if you've got a very high fines content material. And that leads on to this material. So if you do know that you're going to have your project and your working platforms are going to be impacted by moisture, either from the ground or from the sky, you can actually go for a fines-free material. But I still recommend you go for a well-graded granular material, because you still need to have the interaction of the granular particles and the geogrid, because the geogrid itself forms only 0.05% by mass of a working platform. So you've got to get that granular material right, and you've got to understand how that granular material interacts with your geogrid. You know, the geogrid is a high quality controlled product that is used to stabilize and reinforce those granular particles. But without the right granular particles, you have a difficult scenario. If you've got some inferior quality materials on site, your platform is not going to perform as it should do.
Okay, thanks, Craig. I think we'll come on to the geogrid and the geotextile when we look at the case studies.
Yeah.
And so our next section that we're going to look at is stabilized working platforms, and drink in that view, feast your eyes on that view. That's what you've tuned in for, folks. So let's just drink that view in. That is the top of a stabilized high performance composite mat constructed from a layer of cement stabilized soil with a 6F2 granular wearing course on top. So that's the top, which may well look very mundane and boring, but let's take a look through this section of this mat. So this is a chemically stabilized mat, and it uses the existing soil, mixing it with cement or lime to modify its composition and strengthen it. The material cures and becomes something much stiffer than the previous soil that creates a bonded stiff layer of well compacted engineered fill. And then on top of this layer, we specify a layer of geotextile, which is shown there in the blue dash. And that's not a geogrid, it's a geotextile. We'll come on to that a little bit later. And that prevents the fines migration and acts as a marker layer between the two distinct layers there. On top of that geotextile, generally 100 to 200 mil of 6F2 is placed on top, and that acts as a wearing course. And this wearing course is really important as it becomes contaminated with pile arisings that result from concrete spilling out and other rubbish that gets tracked into the mat. This layer can be removed and redressed as part of the proper mat maintenance. And it also allows the machine to sprag and move about on its tracks in opposite directions as it sometimes spins on the spot. And this spragging on the bonded stabilized material would potentially lead to tearing up that bonded soil, and that would result in fissures, which could then fill with water, and then this water could be pumped in and out when it's tracked over, and this repeated pumping action could lead to soft spots in the mat. So this wearing course granular layer is really the magic layer that makes this solution so usable. This stabilized mat design is a very specialist area, and although there's research available on the subject, there is no real established methodology design like there is for, say, a pure crush mat. So here at Andon, we have our own design methodologies, which are based on our own practical research and have been proven in the field to work every time. And it's an effective design methodology, and it's been used to great effect time and time again, and stands up to scrutiny when it's been Cat 3 checked and submitted to approval authorities such as Network Rail on a number of occasions. So if we break this stabilised mat construction process down, it all starts with the preparation of the formation level. Proof rolling and removing the soft spots and backfilling with engineered fill, and then the compaction works are generally carried out with in accordance to specification for Highway Works 600. So that's the bottom layer, the layer that we're starting off. We make sure that we start with some good foundation under our mat. Next is creating the stabilized layer, and sometimes a tractor tows a stabilizing unit as shown. On larger projects, a specialized stabilizing machine is used, but both essentially achieve the same thing, and that is mixing the chemicals in with the soil. So what is happening here is the hopper at the front drops a measured amount of cement or lime into the ground before it's mixed, and then this mixed depth is usually around 300 mil deep. So for stabilized layers which are greater than 300 mil, the first layer is stabilized in situ, and then fill is placed on top of that stabilized layer, and then that fill is then stabilized again in situ. And we make sure that there's an overlapping of the layers as we're biting in with our stabilized gear, just to make sure that we've got a good and sufficient bond between the mat layers. This stabilized layer is compacted to highway spec, and then that happens before the mix begins to harden. So now that's the stabilized layer down. We dress the top with a geotextile and install the wearing course on top. And there we have it, one stabilized mat. What are the benefits and why are they so effective? Well, we'll come on to that a little bit later. So I'll leave that one on a bit of a cliffhanger. But the big risk is the failure of the platform. That is the big associated risk, and pile mats can fail due to a number of reasons. It could be incorrect design solution, the platform type or the sequence of piling, poorly constructed platforms, or the dreaded soft spots. And experience has shown that it's far more likely that rigs will overturn owing to localized problems rather than a general inadequate piling platform thickness across the whole site. And so how do we deal with these soft spots? Well, soft spots are localized areas of the ground which are weaker relative to most of the rest of the site. So the soft spots are areas that are weaker than the soil considered during the design, in a nutshell. And these can be easily identified through proof rolling on site as the soil heaves, and then when it's rolled, then that identifies where the soft spot is. But this method relies on a competent, experienced driver to do a good job. Poorly maintained and poorly maintained platforms, including the proper water maintenance and repairs when necessary. The problems experienced with rig instability are often associated with failure due to inadequate maintenance, and mats should be, where necessary, repaired rather than letting defects and mat contamination to degrade the performance of the mat. So maintenance is really important, and the stitching time really saves 9. So we need to look after and nurture and be kind to our piling platform, and it will look after us. And finally, also, risks are very site specific. So a good knowledge or walkover of the site to identify hazards is important, because it could have large underground structures that require assessment, or slopes. These are all kind of risks that would be associated with that particular project. Overzealous excavation of piling risings as well is also worth mentioning as a risk. I've been on a job where a machine driver in attendance was so keen on keeping a clean mat that they ended up digging up half of the mat in a large area, which then to import a significant amount of 6F2 back in to make sure that we had that minimum thickness maintenance. But maintenance is a key one to get right, because it can be very messy, but it's important to keep that mat in a serviceable condition to ensure that the factor of safety against failure is maintained. So what do we do with these risks now we know about them? We need to understand them and execute good planning to eliminate them as well. Where they cannot be eliminated, we should reduce them and ensure that all relevant parties are aware of those residual risks and the control measures that are in place to mitigate them. And a great start to eliminating the risk is to make sure that the correct mat design is in place, as well as the correct piling design, which is often overlooked, really. So here is a sketch where we had an incident where we were using a CFA. Well, the solution that was chosen for the piling was CFA. So we had a long continuous flight auger that was installing the piles, and we had a stiff layer on top over a soft alluvium, and then we had a very wet saturated layer, which is highlighted in blue there. And as the flight of the auger was spinning round, it was spinning round too quickly as opposed to how deep it was going down, and that's called over-augering or over-flighting. And the output of that is the auger acts as like an Archimedes screw, and it brings up the soil to the top. And when you've got a very wet and saturated layer like that, it was drawing it in and pulling it out, which was essentially removing a layer of the soil that was under there, and that created a soft spot. So perhaps in this instance, because the site investigation was available, highlighting that there was that very soft layer in there, saturated with water, perhaps another foundation solution would have been more appropriate. So it really starts, that's where the elimination of those risks starts, is at the concept of the project in terms of the working platform and also the piles as well. Dealing with water is incredibly important. Usually the formation level is laid to falls and a simple drainage is provided if necessary. Pile mats used over a very short period of time are usually okay without drains, subject to the type of subsoil. However, if the mat is going to be used for an extended period of time, for say 6 weeks or so, then it is worth installing some good drainage, because a soggy platform is not only a messy nightmare to work with, but it's also leads to risk of a rig falling over on the mat. The edge of the platform as well shouldn't be forgotten. It contributes to the strength of the mat as the runoff zone of 2 meters typically from the piling extents is of structural importance. A few solutions are shown here. We've got a simple batter or an embedded mat or a gabion basket or a Kelly block type containment or something similar there. So now we've looked at the mat itself, let's think about location, because after all, implementation risk requires us to look at both the execution risk and also the consequence of failure risk as well. If the rig collapse radius is near a sensitive asset, such as a railway line, then there will be a certain process to go through. Here's an extract from Network Rail guidance document that provides some helpful do's and don'ts when piling to reduce the risk of failure affecting that railway asset. I'm not going to provide a step-by-step guide on this document. However, it's important that we know that this information is out there, and that the piling design or pile mat design adjacent to the rail will more than likely have to be submitted as part of a Form 2, 3 or Form C process, which often includes a Cat 3 independent check by an external organisation as well. If the mat was to fail under load, what does failure look like? There are a number of different mechanisms, but the most common is a punching shear mechanism failure. And here you can see the load is being pushed down and a soil block is punching down into the soil and displacing the soil either side, which is pushed up around that loaded area, which it heaves over the sides of that loaded application area. On the ground, you'll see that soil heave up, and then you'll also witness a large settlement under the load as well. If you do witness this, it's a good idea to stop operations and get well out of the way, because things may be about to get a little bit exciting. Okay, that's enough on the theory. Let's take a look at some real life examples, and over to you, Craig, on our first case study on Geogrid reinforced working platforms.
Thank you. So this particular example is another HS2 project at Old Oak Common. we were in an enviable position to be asked to look at 6 piling rigs and several different ground conditions. So typically the ground condition was made ground, so it was a granular material over a London clay. An average shear strength of the subgrade was a CU of 35 kPa, and that was between 1.8 and 2 tons per cubic meters. In terms of the platform material, it was a good quality, well-graded 6F2 granular material, got an internal angle of friction of 40 degree. So when I mentioned the different qualities of granular material, and they can vary anything from 30 degree up to 45 degree. So we do need to understand what the internal angle of friction of the granular material is when we're going through the analysis process. In this particular case, it was a maximum particle size of 125 millimeters. So we had the large aperture geogrids. In that particular case, the unreinforced, when strictly in accordance with BR 470 was assessed, was 1.64 meters thick, and that would have been installed over a single layer of a separation geotextile. And at 1.64 meters thick, that has to be installed in layers with a maximum compaction thickness to the spec for highway works of 250 millimeters. So you'd have actually been installing over 6 or 7 thicknesses of granular material. So the time taken would have been significant in relation to that granular thickness. The reinforced thickness was 720 millimeters, and we were able to install that in 3 particular layers. The geogrid that was used was a extremely robust polypropylene geogrid from Tenex. The great thing about using the robust polypropylene geogrids is that they act as a spring constant. So Josh, when you talked about the maintenance requirement for platforms, as these platforms are being loaded that got the geogrids in it, it has an element of recovery, so it acts as a spring constant. So it's in old money, it used to be called a self-heal. So it prevents the cracks from opening up in the granular layers. So we use a high modulus geogrid. When we go through the analysis process, we use the stiffness values at a 2% strain. And the values can range anything from 400 to 800 kilonewtons per meter. So as well as being able to use different values for the granular materials, we have access to different qualities of geogrid materials as well. So if the site has a very strict thickness requirement in terms of vertical alignment, we can actually go for a higher grade geogrid than is normally required to reduce the thickness even further. And we can also recommend using a better quality granular material. So because the working platform is a composite of a granular material and a geogrid, we need to make sure that we get the parameters right for those 2 particular products. And as with yourself that you've just mentioned there, Josh, we tend to see the bottom geogrid laid over a geotextile. The geotextile provides that separation and filtration function, whereas the geogrid is providing the reinforcement and stabilization function. And in this particular case, as I mentioned earlier on, your average thickness reduction is between 40 and 60%. This particular case, it was a 56% thickness reduction. So as you can imagine, over an area of 47,000 square meters, that is a significant volume of material that you're not importing into the site or exporting the subgrade material away from the site. So that actually reduced the volume of aggregates taken into site by over 76,000 tons, which was over 3,000 less HGV movements. Now, when you've got a site in an urban area, that has an impact outside of the site as well. So you do save a significant amount of time and money, but you're also reducing the impact on the surrounding infrastructure and the imposition of delays due to the traffic in and out of the site as well. Go to the next one, please. This particular site is Woodwharf Phase 2. So initially we looked at supporting the 12-ton axle loads, and then subsequently we did the assessment on the basis of 2 particular piling rigs. They had different based upon the FPS load cases. In the case of the bower rig, it was actually the handling force that was the worst case. In the case of the soil met rig, the worst case was when it was standing and traveling. So it's not always the case that the operational use of that plant is the worst case load condition. So you need to make sure that you do look at all the FPS load cases in relation to your analysis. The undrained shear strength of the subgrade in that one was 20 kPa. And in this particular case, we used, again, an internal angle of friction of 40 degrees on the capping material, and once again, a maximum particle size of 125 mil. So it's a well-graded granular material used, and the use of the high modulus grids reduced the unreinforced platform thickness from 1.97 meters to just over a meter thick by the inclusion of 3 layers of the high modulus 10x geogrids. So in terms of the benefits to the customer, but also to the sustainability benefits to society, the volume was reduced by just over 8,000 cubic meters. So that equated to 855 HGV movements, 48% thickness reduction. It reduced the cost on site by 30%. And as is the case on most projects now, we did a carbon assessment on that, and it was 53% carbon reduction by using these geogrids. And these are net reduction values. So when we reduce the cost by 30%, that's after the products have been procured by the contractor. So you don't have to reduce the section of a granular material much before the geogrid is paid. So you can typically say, if you're in ground and you're digging out a subgrade material, exporting it away from site and importing granular material, you only really have to reduce thickness by about 50 millimeters to pay for a layer of geogrid. So if you're reducing thickness by half a meter to a meter, it's a significant net cost reduction and a significant net carbon reduction of 2.
Thank you, Craig. So I'm going to talk about the benefits through a case study on Stabilised Parmats through the case of Good Luck Hope project in London. So this was a job next to the Thames in London, and as such we had some quite poor ground parameters. We've got an undrained shear strength of about 13.5 kPa, which is really quite bad, and a relatively large rig with a width of track of 1 meter. The solution that we provided was 6% 450 mil deep OPC stabilized layer that had a 100 mil 6F2 class wearing course on top. So what was so damn good about it? Well, the stabilized material is stronger than that 6F2 when mixed with cement at around 2% or above, and that means that your overall mat depth is smaller to start with. In addition, the material for the mat is already on site because it's in the ground. All you have to do is rock up with some cement and spread it over and mix it. And this means that you don't have to muck away as much soil as well. And you don't have to, all you have to do is import some crushed concrete wearing course. So it's a limited import of materials. And it's also been one of my jobs where we've used it as an impermeable layer to cap off that contaminated ground underneath. And the topsoil placed above the stabilised soil in the permanent condition and used for gardens on the scheme. So all the nasties and in the ground, which was the brownfield site, were kept away from the end user through this method. However, there are some setbacks with water control through that impermeable stabilised layer, as this can cause issue if not properly planned with drainage, etc. Also, a really high cement content can cause difficulties in piling, but from experience, cement contents up to 8% are generally okay. Just forms a very stiff layer at the top. So here we can see a cross section through the mat that was constructed, and that grey stabilised material at the top of the formation level shown below there. And the ground was very challenging here with the very soft soil and being right next to the river. And this job was an example of when we used a specialist software called State Geo to model the pile mat and loadings as another way to ratify the design, because that material is so soft. The failure mechanism here we can see is that beautiful example of that punching shear mechanism, of that load being pushed down and then the soil heaving either side and splitting. It's important to say that software like this is really great for tricky situations and backing up our hand calculations, but as a note of warning, GIGO, garbage in and garbage out, rubbish in, rubbish out. You really need to fully understand what you're doing to ensure that you're getting the correct output, whether you're doing hand calcs or using complex software like this. Once the mat was constructed, it had some plate bearing tests on that to verify the design and construction, and it proved to perform very well. But that plate bearing test, I'm going to lead you onto a crash course in piling platform verification using plate bearing tests. So what is a test? Well, the plate bearing test is essentially trying to model as close as we can the loading that pile mat is going to be put under when the piling rig is going to be operating on there. So that's what we're trying to do. So we use some kentilage, an excavator or a small piece of plant in the pile rig, and we're going to put a plate under there and push off from that kentilage into the mat to a certain pressure to see how that mat performs under that load. Why are they important? Well, they're necessary to verify the design and construction of the mat and bring it into use, because no mat should be used without having been tested and approved beforehand. How many tests to carry out? Generally 1 test per 400 meters squared or so. Sometimes more, sometimes less. It depends on how similar the ground is and the size of the platform as well, how extensive the platform is. The number of tests will be specified on the designer's working platform certificate. And where to test? Tests should be spread evenly across the site, across the mat, and they don't have to be on actual pile positions, but they're generally going to be where the rig is going to track and operate. And we recommend that a retest is carried out on the mat if the mat has been unused for 6 weeks or longer, just to verify that the mat is suitable for use after being out of use for so long and potentially used for storage of stockpiles and other activities, just to kind of provide that proof in the pudding. So let's zoom in and see a close-up of what's actually going on here. So we've got the kentilage on top, and then we've got a load cell beneath that, a hydraulic jack, and then the test plate, which is at the bottom. Usually specify 0.6 meter diameter plates. And underneath that, we've got sand bedding just to make sure that the plate has an even bedding onto the mat, and then the mat itself underneath that as well. This little rig that you can see set up there, that measures the settlement that is occurring under load. So if we look at the kind of results that we are expecting on here, so we've got a couple of great examples. And we're generally looking for less than 10 mil settlement under the track characteristic loadings and a linear relationship between load and settlement. So essentially a relatively straight line that we can see there. Here's another result, which is a really great result that we had on a chemically stabilized mat constructed over that poor soil. And if you look at that, that's less than 10 mil settlement under 140 tons per meter squared. So it's 1,400 kilonewtons per meter squared, and a wonderfully linear relationship between load and settlement. So as the load is being applied, settlement is going up at an even pace. And so testing to the right pressure is very important. It must be specified as part of the design, and what we're trying to do is replicate the loadings from that pile rig as close as possible, and therefore we need to replicate that same pressure bulb. The influence zone of the pressure bulb increases with the load width. So we can see here that we have a 1 meter wide track, a 0.9 meter wide track, and a 0.6 meter diameter plate. If the plate was loaded to the same pressure that is expected to be beneath the track, then the equivalent pressure at depth, it wouldn't be representative. We therefore must increase the plate pressure so that we get the same pressure at depth as we would from that pile rig track. And this is really important when we're looking at weaker soils at depth, because how much greater the pressure needs to be varies depending on the track width, but it can be as high as 3 times the track pressure for a 1 meter wide track. And here, this plate bearing test shows that the upper layers here were really stiff, but then when that stress begins to increase in the softer layers, lower down, as in due to that pressure bulb, then the settlement begins to increase at a higher rate. And that's when we really see the true behavior of how that mat's going to perform, and not how that looks at the very start, where it's very, very stiff. As a comparison, here are some pool results. So we've got test A, which is a homogeneous soil. So that's a soil that's generally the same as through depth, but it's been generally compacted poorly at depth because the settlement's getting worse at a pretty constant rate. Test number B, we've got soft upper layers, but then it tends to stiffen up, and the lower layers are a lot better there, as you can see in the chart. Sometimes this is caused following prolonged water exposure on the top layers, as that top layer softens, or poor compaction of the upper layers. A test result like this can usually be rectified by further proof rolling and compacting that upper layer. So that's not generally a problem. We can fix that. Test C, that's similar to test B, but a little bit worse really. The result is improving, but it's generally failing as deformation is too high. And if we look at that trend line there on test B, that's where we can see that is the true performance of the mat. So once we proof roll it, that's when that's what we would expect to get once it's been proof rolled and retested. So that was your crash course in plate bearing tests, really. Similar designs in working platform world are working platform for cranes, scaffold foundations, short-term hoist bases, and mast climber bases, and haul roads as well. Other uses of Geogrid, which have been used to support piling operations in tight spaces, are stabilized slopes and walls and embankments, for example. This is an area within itself, really. But I thought we'd mention it just to provide some awareness nonetheless. We have got a separate webinar just based on these kind of structures, which is on our YouTube channel. And that concludes our presentation, really. If you want to know more, there's lots of information out there. There's a whole chapter on site roads and working platforms in Temporary Works Principles, which is definitely worth a read. Some other helpful documents listed here. Geosynthetics, we've got a great website with lots of information, news and spec sheets, case studies, technical support from their team, and their website's listed there as well. And that really leads us on to question time. So thank you.